ago for Schlumberger, and like you mentioned, I've worked pretty much all over the globe now, and I picked up a lot of experience and expertise working deep water and offshore type projects internationally in West Africa and Brazil and other places, and we've been able to apply and use a lot of the technologies, specifically fiber optics and some of the other microseismic type work in the U.S. And so even though I'm not standing in the United States and we're not in the U.S., so far when I've gone around and talked to people, regardless of what country we're in, they've been able to glean something from this presentation. And it may not be the very specific application that you have, but they learn something from it, and they realize, well, maybe I can take this piece and we can use it in our field, whether it's an EOR field or whether it's a deep water vertical well. So that's the idea, and that's my objective today, is just to share a little bit about what we're doing in the U.S. The wells are going to look a little different from what you guys do, but maybe something will pique an interest and you can say, I can do this where I work. Okay, so we'll get started. So this is the agenda. I'm going to give just a little bit of background on what our wells look like and the types of wells that I'm going to be talking about, just so everyone is grounded and we all come from the same point of view to get started. Then we'll talk real briefly on fiber optic sensing. How many in the room have used fiber optics for various applications? All right, so over half the room. So we're not going to spend a ton of time talking about fiber optics. Really, I am not a fiber optics expert. We could talk about backscattering. We could talk about Raleigh and Stokes and all of those things, and I'll get way in over my head. But what I'd like to focus on is just how that data is being used to make decisions about our wells. So that's really where I'm going to focus. And then we'll walk through a data set. And so I'll have some fiber optics data, and then I'll have some other bits of information that we've collected on these underground laboratories, and we'll put it all together, and I'll show you what it all looks like when it is laid upon each other. And then ultimately where I want to get to is how are we using all of this data and putting it into our models to make better analysis and better decisions going forward. All right, so that's the plan. We've got a really small group, so if you guys have questions, if you'll just raise a hand as we go, I'll be happy to just answer questions. Okay, so we're going to start with the background. So this is a picture from really close from where my parents and I grew up in western Oklahoma. And in this photo, I think there's 5 drilling rigs. You can see there's actually 8 drilling rigs stacked up in a row here. But this is a very typical scene from unconventional tight gas development in the United States. Our wells are 1,500 to 3,000 meter horizontals, and usually they're right at 1,500 to 2,000 meters vertical depth as well. The well spacing in between these wells that the drilling rigs are drilling will be anywhere from 40 to about 300 meters apart from each other. And then the real key thing, and the reason that the U.S. has been able to increase production in the last few years is this last little bit here, which is this multi-stage fracturing. And so this is the part that I'm responsible for at my company is, how do we do our fracturing treatments? And today we do anywhere from 20 up towards 40 stages, fracturing stages for any one of these wells. And then the last little set of numbers on here are the ones that's important really for this talk that I want you to take away, which is this 3 to 6 clusters per stage. And so that means for every one of those fracturing stages, we have anywhere from 3, sometimes up to 10, but usually 3 to 6 different sets of perforations along the lateral. Okay? All right, so why did I say that was important? Up until about 4 years ago when we did our first one of these underground lab projects, we had a lot of these type of questions. If we've got these 4 sets of perforation clusters, how is our well being fractured? Are the outside clusters having large fractures? Are we only fracturing one single set of clusters and leaving all of this open reservoir unstimulated? Or are we doing a perfect job and all 4 clusters are being stimulated together? So this was a big question. Honestly, we didn't have any idea what was happening. We don't have a good understanding of how the rock affects this. If one set part of the rock is higher stress than another part of the rock, does it move all of the fracturing fluids over? Or likewise, if there's a large amount of natural fractures that present, does that mean all of the fracturing fluid gets stolen into that area of the rock with all the high natural fracturing, and nothing without natural fractures doesn't get treated? So we didn't really have a clear answer to that. And then lastly was, how do we use that information to make better wells, which is how many of these stages, and every stage adds money, and how many clusters do we need to stimulate our wells? So these were some of our core questions that we had. And really, we still have it, but we're getting a lot closer to understanding now. Some of the other key questions that our reservoir engineers struggle with continuously. Do we have any reservoir engineers in the room? A couple? One, two? They revolve, and I'm sure you guys have similar questions. What's the correct landing interval? Should we be landing in, say, a deeper, higher stress area, or should we be landing in a shallow, more porous area? What is our fracture height going to do if we're up here? Will we ever contact the reservoir? Likewise, what should our well spacing be? How many wells do we need in an area? And then finally, but not least, is what is our fracture length and what is the height? And that really drives a lot of these. So we started setting up these underground laboratories, and the company I work for, Devon, we've set up basically one of these labs in almost every one of our fields where we do development style drilling. So anywhere where we have those 8 rigs out there running or more, we do an underground laboratory like this to help answer some of those questions for us. So it'll include vertical wells. So we'll drill wells only to understand what the fracture height is. That's the whole purpose of the well. We'll go in and we'll do some DFITs, diagnostic fracture injection test, as well as we'll do some tracer fractures, and we'll understand what frac height is. And then we'll start doing things like microseismic, and we'll do that either with surface systems, surface geophones, or downhole offset geophones. And that gives us a better understanding of what the fracture azimuth is, as well as the height. And then last but not least, I want to talk about fiber optic sensing. And we're going to spend the next few slides talking about what that is and then how we're using it. Yes, sir?
How big is the scale of the laboratory?
So in here, this would be like for a typical development, 1,000 meters by 1,000 meters, or 1,500 meters, something like that.
And usually it is in a field?
Mm-hmm. Yeah. So it's so if we have a field and we're going to drill, say, 400 or 500 wells in an area, so we'll try to pick the optimal place in the middle, or maybe when we get started, it may not be the optimal place, to set up a lab like this, where we collect lots and lots of data to help us understand what's happening with our fractures. So the fiber is there. We're going to try to get the number of fractures and the relative size of each one of these fractures. And if we have 4 fractures being created, or if we have 1 being created, it makes a big difference on what the size of those fractures are. So we need to count them. Okay, so fiber optic sensing. There was a few hands that didn't go up, so I'll talk about the basics real quick. Really, we're using 2 technologies: distributed temperature, which you'll see distributed temperature all over the Middle East, Oman included. This is a very common tool today for doing all sorts of things: EOR, measuring matrix acidizing, measuring gas lift optimization. All of these things were the traditional uses of it. It's been around for almost 20 years. The other bit, which is newer, is distributed acoustic sensing, which also uses a fiber. It's a different type of fiber, but it's a very similar type measurement. You're shining a infrared laser, a light down a fiber optic line. You're looking for the refracted light that comes back. From the difference in the waveform, you can ascertain how much acoustic energy is happening all along the fiber, similar like we do with temperature. The key takeaway message, and we'll get it here, is for those that haven't been around fiber before, one of the misunderstandings that people have is that there's some gadget at the end of the fiber, and we're using fiber for only communicating with the gadget. That's not at all what's happening. So the fiber optic line itself is the measurement device. And so that means that we get a measurement all the way from the surface at the tree to the very end of the well. Okay? Okay, so for our wells, I talked about what the well looks like. It's a 1,500 meter vertical depth to 1,500 meter lateral length. And for the application that we're going to be watching fracturing treatments with, we need to permanently install the fiber optic on the outside of casing. And so that's what you see a picture here. This is from a drilling rig in Oklahoma, close to where those other rigs were. And you can see the yellow fiber being strapped to the outside of the casing string. This is a 5.5-inch casing, and it has a special clamp put on the outside of it as well. Here's a better picture of that clamp itself. So we install that on the outside of casing, run it all the way down to the bottom of the well. It's a long string, so it's not a liner. There's a bunch of extra steps we have to take to make sure it gets into the ground without being damaged. So we spend extra amount of time doing hole cleaning, understanding what our drag coefficients are going to be in these wells, making sure, do we need to run reamers or not? Do we have any type of swelling problems or clays? All of those sort of things you've got to do ×3 for an installation like this compared to a normal well, especially with these long horizontals. The other piece of information that is different is I showed you all of those perforation clusters, and now we've put a fiber on the outside of the casing. And so job number one is to make sure that we don't blow a hole in our fiber with our perforating guns, right? So has anyone ran fiber in a horizontal well like this before? So when we first got started, I don't know what approach you guys have taken, but we used sleeve systems, like ball drop sleeve systems. And so we would just plug up part of the sleeve that was going to have the fiber on the side, the ball shifts the sleeve, and you go the other way. So that's where we started. That was successful for us, but it was very expensive, and it was really time consuming to do that. The other thing that we found is when you run those sleeve systems, all of your perforations, they're set. So if you learn something on the first frac stage, you're not going to be able to change it and do something different on the second stage because everything's cemented in the ground. So since that time, our next 7 wells have all been just cemented, perforated, what we call plug and perf type systems. But what we're doing is we're using a magnetic wireline tool that gets tractored to the bottom of the well, and then we use these special clamps to give us a magnetic signal about where the fiber is. And so as we're pulling back out of the well, we're stopping and we're doing stations, that magnetic tool is rotating around and it tells us exactly what side of the casing the fiber is on. So we've been able to complete all of the remaining wells using weighted perforating guns. Now that we know where the fiber is, we just shoot in the opposite direction. And we haven't perforated one yet. So we've done really good with that. And it's actually cheaper, it allows you flexibility, and honestly, this mimics our true completion a lot closer, which is really what we want. We want a test that mimics what we do in the real world. Any questions on the installation?
And it will be difficult to just put the cable on one side. It's not something that you can control. It is going to twist them.
Mm-hmm. Yeah. Yeah, it twists. It doesn't twist fast, we found. So that was one of our concerns when we first got started, was how fast do we find that it's going to be twisted around the outside. It's pretty slow. In fact, we've seen a couple laterals where it's along the same side for the entire lateral. Maybe plus or minus 10 degrees. But it goes this way and then that way a little bit, but it didn't do a true twist. So it doesn't change a lot. In fact, you could probably make do with I'd say 1 station every 300 meters almost to get a good indication of where it is.
You will be able to go in detail soon. You will be able to know where the orientation of the cable or the place of the cable before you cemented it, or you have to wait?
No, we do it afterwards. So we wait until the cement is set, the drilling rig has left location, and then later, whenever, we'll just do it with a wireline rig and just tractor in later on. So we wait until later on. It's a good question, though.
But it will limit.
Well, there was a question how long it will take
to perforate? I mean, how many runs can we perforate per day, for example?
So it takes about 2 hours to perforate, average, for a well like this.
How long?
So perforating depths are, it would be 4,000 meters, something like that.
No, I mean, if my target is
It's one drive.
20 or 37 meters. So one drive I can go and perforate this 30 meters per hour.
Yeah. So most of these clusters, let's back up a step. These are great questions. Most of these clusters that you see are only 0.3 meters, 1 foot. So we'll just put, your gun system is this long, 4 feet long, 1.5 meters, and you'll just shoot, boom, boom, boom.
You shoot clusters. Okay.
That's right. So we shoot clusters. Because all of the fractures that are going to be created are transverse fractures anyway. We don't need long perforations. All right, I want to show you some of the data. And this is the acoustics data from a fiber optic well. And so if you haven't looked at fiber optic data before, this is called a waterfall chart. And this is, it's going to jump around a little bit, so excuse the quality. I actually collected this on a location during a frac job when I was out there just capturing the screen. But you've got the depth along the bottom here. So the heel is over here. The toe of the well is over here. And what I've shown now are 4 clusters. This is the real-time data up at the top. And this is a rolling history of everything up here. So it just falls down. It's called a waterfall chart. And so what you can start to see at these 4 perforation clusters is how much noise is happening at each one of the clusters. All of the areas that are blue are pretty quiet. And then you've got this loud, almost screaming sound, rah, really loud, right at the perforation clusters themselves. And they create this large acoustic energy and large acoustic noise. And so now we can start to say, yeah, we've got noise happening at these upper clusters, but we've got one cluster right here in the middle that is very quiet. It has almost no noise associated with it. So when we did this the first time, out on location, watching it, it was completely eye-opening. We had no idea what was happening. It was amazing. I mean, it was one of those things where the first time you were able to see what was actually going on downhole, that's what was happening here. And it's going to jump in just a minute.
So what is going on as a frac job? Or what?
Yeah, so right now we're pumping a frac job from surface. It's very high rate. It's a slick water job, so it's just water and polyacrylamide plus proppant.
Is this distance related to the distance between the oil bore and inside the formation, or just a scale?
So this distance here is just along the lateral. So this would be a range of approximately 300 meters along the lateral. And we're only taking the measurement right at the wellbore. So we don't know what's happening away. So what you see, excuse that for just a minute, what you see falling down here is this is not distance, this is just time. It's just a history of how things are happening. It's just a time. But what we show, and this is a unique thing that we saw for the first time also, is some of those plugs that we use to separate one stage from the stage below it failed. And so you see these loud ringing sounds happening here. And now all of a sudden we're starting to have noise down at the perforations that were below the stage that we're fracturing.
How long did you record the acoustic data for?
How long did we record it?
For each stage?
So we recorded it continuously almost for 5 days throughout the fracture.
Headache to control the size of the data, I believe.
The size of the, yes. So this type of data, we're talking terabytes of data. And we don't move this data over the internet. This data gets moved in a giant box because it's just too much information.
So did you have true acoustic, amplitude, phase, and frequency, or was it just the noise recording?
We had all the raw data recording, and what we ended up with was just the, I'm going to misspeak, just the overall magnitude, I think, is what we ended up with our historical files that we collected. So that's what the data that we looks like on a fracturing treatment.
Yes. Do you also use the data for also seismic profiling at the end, or you just use it for just operation time?
So what we've used this acoustics data for on this well is only the operational aspects of the fracturing treatment. We're just now starting to use fiber optics for seismic acquisition as well. That's a different talk, though.
Oh, but can you still at the same mode? I mean, with the same DAS?
You can, but not while you're doing a fracturing treatment. What we've seen with the data so far, when we do that, it's prior to a well being stimulated at all, and we'll do some either check shots or walkaways with vibration units on surface, and then we have collected some data that we think ultimately this equipment can be used for good seismic data.
what we actually can interpret from the frequency and the intensity of the noise.
Yeah.
Yeah, what we can interpret from both.
So hey, hold that thought for just a minute. I'm going to try to get to that point. That's a good question. That's a lead-in. So what I want to do now is talk a little bit about what all of the fiber data that we just talked about, how does it look compared to the other types of data from the underground laboratory that we talked through in the first. Okay, so this is one of the stages from one of our wells. And it's a pretty typical type of stage. You see a lot of noise happening at the uppermost cluster, and then nothing happening at the second cluster. The third and fourth have some amount of noise associated with them, which indicates that we had some sort of fracture being propagated in all of those fractures. What we do with this data is we collect it and look at it over the entire length of the fracturing stage, and then we integrate that with the material balance, that we know what we were pumping all along that stage, how much sand and water was going on at each interval of time. And then we come up with the total amount of proppant and fluids that went into each one of those clusters. All right, this is the distributed temperature data, and you guys may be familiar with DTS. It's very common these days. Blue indicates cooler temperatures, and this fracturing treatment happened in January in Oklahoma, so it was very, very cold water. And so you can see very big cooling signatures associated with the uppermost cluster, and then the third and the fourth, with very little cooling happening at the second cluster. It corresponds very well to that acoustics data that we collected. Okay, the last piece of information that was collected during the frac job itself was a microseismic. And so this was a surface microseismic setup. And so this is about 1 mile, 1,600 kilometers here. There's our well bore. And then we laid out geophones in these star patterned array. This is a trademark from a specific microseismic company to do it this way. There was about 1,500 geophones laid out all over the ground. In fact, the sensor's buried only like an inch or two underground. And then we collect microseisms from that. And so what I'm showing you here is that same exact frac stage that we saw with the fiber optic data. But now you can see that we have a really dominant fracture up here at the uppermost, at the heel. And then we have a blank spot where we know we weren't treating it with the fiber optic data. And then we have a second and a third down here in our last two clusters. So at this point, all of the data starts to line up. We gain confidence in using acoustics data to start to measure what we're doing here. After the well was fracked, we ran in with another logging tool to log the radioactive tracers that we pumped into the well. And what we're looking for here is the yellow, the antimony associated with it. And so you can see we had a big tracer up here, a little bit here, big peaks down here and down here. One thing that we learned out of this is we cannot trust tracers, and we've seen this a couple times now, to give us any type of quantitative measurement associated with where the fractures are going. Okay?
Do you pump it at the flash stage or at the last proppant stage?
On our jobs, we'll pump them almost continuously while we're pumping proppant.
So
So it's throughout the job.
Okay.
So not continuous is the wrong word, but throughout the job.
Okay.
So and at discrete points. And then finally, since this data set comes from our very first well, we also wanted to do a true production log afterwards. So this is a third generation kind of production logging tool. And you can see this is the exact same stage. You can see the cluster 1, which was our dominant fracture. It contributes the most to the well's production, 4% of the well's production. Cluster 2 wasn't making any gas to speak of. Cluster 3 and 4, a smaller amount of gas. So everything kind of lines up. And this type of data that we collected on our first well gave us confidence to do this over and over and over again and make this a core piece of our underground laboratories. All right, so I'm going to shift gears. We'll talk a little bit about how the data is being used now that I've shown you kind of what it looks like. So this is a cartoon image from Halliburton, but it does a very good job of displaying what we're trying to understand here. So we take that fiber optic data, and then ultimately we're going to convert it into a model to understand how big those fractures are that we're creating. And so you can see, similar to the data set that we showed, anytime you have these larger acoustic noises, ultimately we can do some calculus on that and understand what the material balance is associated with it. And what we've been able to do in the last couple of years is use some commercial hydraulic fracturing models, which were made for another purpose, but they allow you to do almost exactly the same thing. Throughout the fracturing job, you can shut off clusters in these new models to get a good representation of what the fractures look like. And let's go back a second. What I'm depicting here is 4 individual clusters. I know they're hard to see it, but there's actually 4 discrete fractures, planar fractures here. This is not the same stage we saw before, but it's just here for representation. And what I'm going to do on the next slide is I'm going to take one of these fractures that's in the middle and show you what that looks like when we turn it sideways and just look at half of it. Okay, so this slide shows you a before and after. All right, so let's use our imagination, and let's say we never collected the fiber optic data. So we just ran a model on basically what we saw from surface for pressures and rates. If we use our imagination, this is what the model predicted that our fracture was going to look like. All right, so I've stripped off the scale here, but you could say that this is about 300 meters long and maybe 30 meters high. But it's a significant fracture that the model predicted that we were creating. However, once we used the data and we adjusted the model and constrained it to what we actually saw in the field, now you can see that we have a very insignificant fracture. In all honesty, it shows that this fracture would not produce anything. So it's quite a different story.
But what about material balance? I mean, do you like adjust click off or what to make such moves? It's like a big difference.
Yeah, we're not to the point yet where we can adjust leak off to make this happen. But what we can do is basically shut off all fluids about halfway through a frac stage and say that cluster gets no more fluids.
Okay, so they balance it to a different...
It balances it, it pushes all the fluids to a different cluster. That's right.
Okay, so from this data we understand the model or which zone is contributing much. I mean, can we use this data to improve our efficiency in fracture?
Yeah, yeah. So some of the very early things that we've learned is our stages, they can't be very long because we just cannot treat all of those clusters. So since this data set, for example, in this field, we've doubled the number of stages that we have in our wells because the stages just can't be very long. We've also reduced the number of perforation clusters because we know that they can't be treated.
That's what they were
That's right. So we did that almost immediately. The thing that came later that we didn't know about going into the well was how valuable this information was going to be to our reservoir engineers. Our reservoir engineers had been making some big assumptions all along on their models. And I've shown a screenshot of RTA from Harmony here. But regardless of if we're doing advanced simulation or if we're just using an analytical tool, we have to make an assumption on the number of fractures in our well. And up until this point, it was a wild guess. You know, we had 80 clusters open, and we were guessing maybe 60 of them are making fractures. Now we actually had a very good tool to measure exactly how many those are. And so this has been very important for us. And I'll show you the economics for that. Really, that number of fractures drives our interpretation of what the permeability on these type formations are. It's not a unique solution. So now that we can constrain one of those variables, the number of fractures, it gives us a better understanding of what the permeability is. And ultimately, it's going to drive us to how many wells do we need in a section. So our understanding of perm will take us from doing something incorrectly like this and hopefully putting the wells close by so that we're ultimately draining the entire reservoir. That's the idea. So this is real data from one of our fields that we did one of these underground labs in. And so what I'm going to show you here, it says oil and gas rate. It's been stripped of its units, but this was basically an oil chart. And so we looked at 4 different scenarios here. And for us, 2 wells per section, a section is 1 mile. So this is a very standard measurement in the United States of how we measure things out. So basically this was saying that we need wells every 1,500 meters or so apart from each other, all the way down to here 6 wells per section, which would have been, let me do the math, maybe 200 meters apart from each other. And so all of these wells come on with similar initial production, but quickly over time, over the first 3 to 4 years, they separate quite a bit. And so we do this type of economics, or this type of rate versus time, so that we can understand the economics of depleting the reservoir versus putting the optimal number of wells in there. And so for our base case for this field, before we collected any type of fiber optics data, told us that an optimal net present value for the number of wells was 6. So we needed approximately 6 wells in every one of our sections to help drain the reservoir. Once we took all of that fiber data and we plugged it back into the reservoir models, at least the analytical tools, it moved our answer to now that we can drain, well, I'm sorry, I got them backwards. This was what it was before, and now it's up here, but originally we could have drained with only 3.5. And so the value of the fiber data in itself, we could very quickly calculate. For us, this was well over $1 million for every section, and my company had over 100 sections to develop in this area. So that's pretty easy math for most engineers.
We will use the data for fraction. Do we get also data during the production or?
Oh yeah, yeah. I haven't talked about that.
Yeah.
And that data itself has been it's been around a lot longer, right? So we've been using DTS, for example, to monitor production for some time. But yeah, we're doing that as well. So all of these wells have survived all the way through the fracturing treatment and are still, today I could bring it up on my laptop, look at the DTS profile across the well. So that is a side benefit for sure. It's a good point. Okay, one last slide, just some closing comments to leave you with. For us, using fiber optic sensing, and this is a new application of fiber optic sensing in our eyes, it's been a powerful addition to this underground laboratory that we've been setting up. It's really become the standard way to operate. And then lastly, not only the fiber, but when you integrate that with a bunch of other types of measurements, so we talked about microseismic, we talked about tracers, we talked about DTS and DAS. You start putting all of these together and the total equals more than all the parts. You know, they definitely build on each other and build on your understanding of doing them. So that's the point that I make here at the last, integration of advanced fracturing measurements.